All right, so we'll continue in section 12.3, starting with how do you integrate a vector function. So let the vector function f of t have components f sub 1 of t, comma f sub 2 of t, comma f sub 3 of t, where f1 of t, f2 of t, and f3 of t are continuous on the closed interval from a to b. So I'm going to start with the definite integral, and then I'll just write down how you would do the indefinite integral, which is going to be basically the same thing that we would do for the definite integral, with the exception we don't have any bounds at which to evaluate. So then the integral from a to b of the vector function f of t with respect to t equals, I'm going to go to the next line because I don't think I can squeeze this on this page. The integral from a to b of f1 of t with respect to t. I'm just going to have to use I, j, and k. I plus the integral from a to b. You can use the pointed brackets. I just forgot. I put a parentheses over here instead of a pointed bracket. So I just decided I'm going to use I, j, and k. But if you want to drop the I, j, and k, you can use pointed brackets and put commas in between. F2 of t dt j plus the integral from a to b of f3 of t with respect to t. Okay. So if you know how to do an integral, then you know how to do an integral of a vector function. It's just that your answer, you're going to take the integral of each one of the component functions, and your answer is still going to be a vector with those same those things in the same place, but now you evaluate the integrals of them. Sorry about that. All right, now if f of t is just continuous, so here I have continuous on AB, but if f of t is just continuous, then we can talk about doing the indefinite integral. And in this scenario, now I'm going to use the brackets this time. It's just going to be the integral of the indefinite integral of each one of your component functions. So f1 of t with respect to t, comma, the integral of f2 of t with respect to t, comma, the integral of f3 of t with respect to t. And that's the vector you get there. All right, so now we talked about derivatives and integrals of vector functions, so we're ready to go ahead and do some examples. So I'm going to start on page 776. We'll do number 24, which says, in exercises 22 through 27, find the velocity, speed, and acceleration of an object having the given position function. And they give us RT equals e to the negative t, comma, e to the negative t. All right. So they asked for velocity, speed, and acceleration. So velocity, v of t, is just equal to r prime of t. So we're just going to take the derivative of each one of these, all right, which gives us, remember it's still a vector, so don't forget about that, negative e to the negative t, comma, negative e to the negative t. And it asks for speed next, just because speed is the magnitude of your velocity. And don't let the fact that you have t's in there deter you. You still do things the exact same way as you usually would. So this equals the square root of this first component squared. And we square that where the negative times the negative is going to go away. And then e to the, we're going to have e to the negative 2t there from squaring this. This is e to the negative 2t. And then same thing here, plus e to the negative 2t. And we can simplify that, so I will. You don't have to, but this is 2e to the negative 2t, which is also the same as, so here this is 2e to the t, 2e to the negative t, sorry, and then that thing squared. So this is the same as the square root of 2. Oops, what did I say? That's e to the, I should have put it on the outside. So the square root of 2 and then times e to the negative t. And lastly, they ask for acceleration. So a of t equals the derivative of velocity, or r double prime of t, whichever way you want to look at it. So the derivative of our velocity vector, this vector right here, just gives us the derivative of this is e to the negative t, and the derivative of this is e to the negative t. All right, so nothing fancy there, just making sure that you maintain your vector brackets or your IJK, whatever it is that you're using when you go through that process. All right, next, let's look at number 32. I'm going to go to the next page for that one, so I'll stop for a second so you can get this written down. Okay. So number 32 says, in exercises 28 through 32, find the position, velocity, and speed of an object having the given acceleration, initial velocity, and initial position. All right, so they give us acceleration here. They tell us that a of t equals, so one thing to be cognizant of is that this a of t, we only see an I and a j in there, but you have to look at the entire problem, and there's a k in the initial velocity. So I need my a of t to have a k component as well if I'm going to use these pointer brackets. So e to the t and then e to the negative t, e to the t, e to the negative t, and then 0. The initial velocity they give us, v sub 0. So now when we are talking about like velocity and position, now when you see a subscript of 0, that's the same as time t equals 0. Unless you're told otherwise, but I don't think that you would encounter that at all. The convention is that the subscript 0 means that time t equals 0. They tell us v sub 0 equals the vector. I lost it, sorry, 1 second. 1, negative 1, square root of 2. 1, negative 1, square root of 2. And they told us that the initial position, r sub 0, equals the vector 1, 1, 0. All right, so they told us to find the position, velocity, and speed. So we're starting with the acceleration, and we want to integrate the acceleration so that we can find velocity. So v of t is equal to the integral of a of t with respect to t. So we're going to just integrate what we have here, and that'll give us what our velocity is. But this is an indefinite integral, so we're still going to have our constants of integration for each one of the components. So this is going to be equal to the antiderivative e to the t is just e to the t, and then plus c. We're going to do plus c1 because we're going to have three different c's. And if you want to, you can make the c1, c2, and c3 a separate vector. It doesn't matter which way you write it. Then antiderivative here, negative e to the negative t plus c2. And then antiderivative here is 0 plus c3. So that's just going to be c3 right there. Now, because we have an initial velocity, we can figure out what our c1, our c2, and our c3 are. So we're going to use that information. So this right here tells us that v of 0 is that. So let's just write that here. 1, negative 1, square root of 2 equals v of 0. We were told that from the very beginning. Now we have a v of t, so we're going to plug 0 into here and set those equal to one another so we can solve for c1, c2, and c3. So according to our given information, this is v of 0. According to what we did, v of 0 is also e to the 0 plus c1. So that is 1 plus c1. Then comma negative e to the 0. So negative 1 plus c2. And comma c3. So now this vector is equal to that vector. Says that corresponding components are equal to one another. So we have a system of equations. 1 equals 1 plus c1, which tells us that c1 equals 0. This says negative 1 equals negative 1 plus c2. Which tells us that c2 is also equal to 0. And this tells us that the square root of 2 is equal to c3. So c3 is equal to square root of 2. And now we actually have our velocity vector. So v of t is equal to e to the t plus 0. So just e to the t there. Negative e to the negative t. Negative e to the negative t plus 0. And then c3, which is just square root of 2. So that's our velocity vector. And now we just need to find our position vector, which is the last thing they asked for.
Yeah, they asked for speed as well, sorry.
So while we're here with velocity, let's just go ahead and find the speed. So the speed is the magnitude of velocity, which equals the square root of e to the t squared. So that is e to the 2t, and then plus negative e to the negative t squared. That is e to the negative 2t. And then the square root of 2 squared plus 2. This actually simplifies. You don't have to simplify it, but it does. This under here is a perfect square. It is e to the t plus e to the negative t quantity squared. So it just ends up that we have e to the t plus e to the negative t is our speed. And now, lastly, we are looking for our position. So RT is equal to the integral of our velocity v of t that we found. So now we're going to integrate this vector right here. And I'm going to go to the next line so I have space for my constants of integration. So the integral of e to the t is e to the t plus some c1. And if you want to, you can use d1, or if you're going to get confused between your c values that you can use d1, d2, d3, but it doesn't matter. You can certainly use those same things. We use c all the time, no matter what problem we're doing in Calculus 1, we can do the same thing here. Then the antiderivative of negative e to the negative t is just e to the negative t plus c2. And then antiderivative of square root of 2 is square root of t times square root of 2 plus c3. So now what I'm going to do is my initial position we were given that 1, 1, 0 equals r of 0. And then we found r to be this. So we're going to take zeros and plug them in here for t. And we'll get e to the 0, which is 1 plus c1. E to the negative 0, which is 1 plus c2. And then 0 plus c3, which tells us, so same thing that we got before, 1 equals 1 plus c1, tells us c1 equals 0. Oops, sorry, can't see that. And then 1 plus c2, 1 equals 1 plus c2, tells us c2 equals 0. And lastly, 0 equals c3. So we plug these in for those c values right there, and we get r of t just equals e to the t, comma, e to the negative t, comma, t times square root of 2. All right, so we'll stop this video there, and then in the next video, I'll do a couple more examples from this section.